So in one of the previous class we sort of mentioned the spring potential energy, that is the potential energy which is stored by a spring which is being compressed or elongated by a length x. So if we elongate the spring by length x, we said that the potential energy the spring stores now is half kx squared. Well, what we mean by it stores this amount of energy is that it can do this amount of work on any system, or it can produce this amount of work. But to go from here to here, we need to do work on the spring. And if we do work on the spring, that increases the potential energy of the spring from 0 to some value, and then the spring is in a state to do work. We are not really losing work in between. To really derive this formula, let's understand Hooke's law. So according to Hooke's law, the force produced by the spring is given as minus kx, and what we mean by that is that if, let me redraw the diagram, if this is the spring and you stretch it, let's say this is the x-axis direction by a distance x, then we know that if we consider this part, the force is going to be in this direction because spring is going to pull it backwards, and the x is in this direction, right? And that's why we have this negative sign, which is confusing to some of us. The force is in the opposite direction compared to the direction in which the spring has been stretched. So this is the direction of stretch, and opposite is the direction of force. So let's calculate the work we have to do to take the spring from here to here, or stretch the spring from here to here. Okay, so let's say we start in the unstretched position, and we are somewhere in a place when we have stretched the spring by, let's say, u, by a length u. For this particular state, we know the spring will be producing a force minus ku, but we will actually be producing we are trying to stretch it in this direction, so the force we are providing is going to be ku, because the force we are providing is going to be in this direction. Spring is trying to oppose it in the other direction. Okay, so this is the force which we have to apply at any point of time when the stretch is u. We know the small amount of work we are going to do when we stretch it from u to u plus du, where du is a small amount, is going to be ku times du. Does it make sense? Work done is equal to force multiplied by the distance. Distance has been chosen small so that sort of we assume that this force stays constant through this small distance. This is what we do in differential calculus. Now to calculate the total work, we integrate this from 0 to x. Let's say we stretch it from 0 to x. So we stretch it from 0 to x, and that gives us fu du. Du is just an integrating variable, and that gives us I'm sorry, this should be actually ku dot du, and if you integrate that, w turns out to be half kx square. If it's not clear, I will just put u square and apply the limits, and then it is half kx square. So this is PE, or potential energy gain, in the spring. which is also same as work done on the spring, right? So that is the basics.